I'm Harshit Motwani. I'm a postdoctoral fellow in the Department of Computer Science. I am actually a mathematician. I did my PhD in algebraic geometry and its application to computer science, and from Belgium. And today I will give you basics of number theory, as I've been told that you require these things for your blockchain course. So I'll cover all the mathematical part, all the theorems, proofs, and I'll explain you everything mathematically that you'll require for the course. And for any of the doubts that you might have from the number theory or from algebra or from anything that you are facing in your blockchain course, you can just write a mail to me, or I'll be happy to clear them. So this lecture is essentially divided into let's see how fast we can go. Maybe we can make it into 2 or 3 sessions, or if you know everything and you're comfortable with the pace, then we'll cover a lot of material today. So the main idea is to reach to the point of primitive roots. Like I was seeing the lecture of previous class, and I think you are using primitive roots in one of the protocols, cryptographic protocols. But we need to develop the theory for it. We cannot just use it as a black box, because when you need proofs for things when you do it in cryptocurrency. And I'm following this particular book, Elementary Number Theory by David Burton. And the content basically, I'll introduce all the notations and definitions. I'm not assuming anything. I'm starting with division algorithm that you might have seen since your middle school or primary school or high school, depending on your background. And in this entire lecture, please feel free to stop me at any point you feel that something is not clear to you, or if there's some difficulty, feel free to use chat, and you can also like turn on the video and ask the questions, whatever is more comfortable for you. So just before I start, I want to ask if there are any questions regarding this. I'll make all these lecture notes available to you, and there will be lots of exercises in between the lectures. So like I will not give you a separate exercise sheet, but like I'll just give you these lecture notes. Just try all these exercises. These are really important exercises. These are not very difficult, but it will help you to develop intuition for math and for number theory. And this lecture will be more like math lecture, pure math lecture. It will be of a different flavor than your other lectures. Let me know if everything is fine so that I can proceed. Or if you have any questions, please feel free. Just write in the chat if everything is fine, yes, so that I can proceed. And I want it to be interactive lecture. Like, please ask questions and don't be shy or afraid for asking things. Is it fine? Okay. No, there will not be any deadlines. It's just like it's good for your concept clearing thing, and it's good if you solve these things. It will help you in the blockchain course, because you might get something in the exams. If the concept is clear, then it will be much easier for you. Otherwise, you might face some difficulties. I don't think I'm not putting any deadlines for the exercises, but like I'll definitely suggest you to solve these things, because it will help you understand the proofs, and you will enjoy the process more if you do this. It's very the exercises are very you will see, it's not very hard. I'm just building up slowly. I'm not putting anything that I'm not introducing. So if it is fine, then I'm proceeding. Like first of all, number theory is very fun subject. It's like enjoy the subject more, and then you will learn the concepts. Just don't take it as theorem definition proof, theorem definition proof. Like just try to understand things, and it's a very fun subject. So just wanted to say that before I start. So first I'll start with, first of all, everyone can read the things written in the screen. Everyone can see the screen, right? Just say yes or no. Okay, cool. So and this size is fine, or should I zoom in? Okay, cool. So, and you can also see the pointer, right? Yeah, okay, cool. So first I will start with quick review and notations, like the notations that I'll be using in this lecture. And I think this notation is also coinciding with the blockchain course that you have been doing. So first I will start with the basic division algorithm that you know. So what division algorithm is? So suppose we are given two integers and we want to divide one by another. So we just assume that our b is not equals to 0. I'll just highlight the important thing. We will not divide anything by 0. That's a sin in math and science. You never do that. So we assume that b is non-zero. So if I'm given two integers a and b with b non-zero, then there exists unique integers q and r, which we call quotient and remainder, such that you can write a in this form: a is equals to qb plus r, where r is from varying from 0 to less than mod b. The mod b is there because I'm not assuming that the sign on b, like I'm writing it in the full generality. Generally, people assume that b is positive and then they just don't write mod b here. And how do you do this? You do this via via the division algorithm that like you have been doing that from your childhood. So that it's just a formal way of writing things. And then there's some notation. We say that b is said to be divisible by a, like here I'm switching a and b, and now divisor is a, where a is non-zero. Again, we'll never divide with anything zero. That is a sin. You don't do that. So a is non-zero and you want to divide b with a. So if a divides b, then we write something like this: a this this line and then b. This notation is very common in math, and I think you will be also using that in your blockchain lecture. So what this means is, like, there exists an integer c such that b is equals to ac. Just keep this notation in mind. This is just notation, nothing else. And when something is not divisible, we write something like this: a is not divisible by b. B is not divisible by a. Sorry, b is not divisible by a. And some of the examples, like 2 divides 4, 3 doesn't divide 4, 3 doesn't divide 4, and you can just keep on doing this. I hope everything is clear to you here in this slide. I think this is the most easy slide, but let me know if there's any confusion with the notations or anything, because I'll be using this notation throughout. So I think I'll proceed. So first exercise, again, take it as homework. So what the exercise is, what I'm asking you to do is, like, if a divides b and if a divides c, then I'm saying a divides all integer linear combinations of b and c. That for any integer x and y, a should divide this. I will also give you a hint. Just use the above notation and it becomes much clearer. Just use these things. Just use this property. Just try to use the division algorithm and this property, and then it's much clearer. Just you have to just follow the definition, and this exercise will be done. Take this exercise because this will be used. This will be used a lot in the later things. I will share the lecture notes. You don't need to note it down. And now I will go to the greatest common divisor. First of all, everything is clear here. There are any doubts? So, like, I will keep on asking it. So don't feel shy or afraid to ask anything. If everything is clear, then I'm proceeding. So, okay. So I'll go to the next part, which is greatest common divisor. So what is greatest common divisor? So if you have two integers, a and b, and at least one of them to be non-zero, we assume that at least one of them is non-zero. And then the greatest common divisor of a and b is denoted by GCD AB. This symbol is used. GCD of AB is a positive integer d, as the name suggests. Can you say it again? Is there a doubt? Okay, I think there's just oh, okay, fine. So GCD of the name suggests the greatest common divisor. So you have a and b, and I want to find the largest number that divides this. That's why it's called greatest common divisor. And how it is, like, and how you formally define it mathematically is, like, there is a positive integer d such that d divides both a and b. And if there exists another integer c such that if c divides a and c divides b, then that number should be less than d. This is exactly what the name is saying in English, greatest common divisor. And this is the way you formalize things in maths and also in CS and also in all the formal sciences. So this is something that you have to get accustomed to when you're doing theoretical CS or maths or any of the hard sciences. So I hope this definition is clear. Just few examples. GCD of 2, 4 is 2. Like 2 and 4, 2 can divide both, and it's the largest number that can divide it. GCD of 2, 3 is 1. They are relatively prime. There's nothing other than 1 that can divide these two numbers, and so on and so forth. So once we have this greatest common divisor, first of all, is this clear? Have you seen this before? Just say yes or no, or if you have any doubt. Okay, I'll assume yes. So now I'll give you one of the most important identities. This will be used throughout your course of blockchain time and again, and this will be used throughout my lecture also. This is Bezu's identity. So this is suppose you're given two numbers A and B, and we know that the GCD of these two numbers is D. Then we know that there exist some integers x and y such that you can write D in this form. Just keep this property in mind. This is one of the most important things that I'm going to say. Um, so like you can always write, you can always find integers x and y such that this holds. Now I'm going to do the proof, but like let me know if this statement is clear to you or not, or if you have any doubts for this statement. Um, okay, okay. I think not. So then I'll go with the proof. So what we'll do for the proof is we'll take a set S, and set S consists of all integers of this form AU plus BV, where all of these are positive, and we assume that U and V are integers. So we take all positive integer combinations of A and B. This set is a set of integers and a set of positive integers, natural numbers. And if you remember the axioms of natural numbers, there is something called well ordering principle that says that if you have a set of natural numbers, then you have something, then you can find a smallest element in this set. This is one of the principles that we assume for natural numbers. So by well ordering principle, we say that so first of all, this set is non-empty. Why this set is non-empty? You can just put anything u and v, and there exists something. You can just put u to be 1 and you can put v to be 0, and then you have a in the set. You put u to be 0 and you put v to be 1, you have b in the set. So this set is non-empty. So now we can apply in well ordering principle, because well ordering principle only works for non-empty set. So well ordering principle says that you must have a smallest element in this, and we say that let's say that the smallest element is d. So we just assume that that smallest element is d. And now we have a candidate thing. Now we want to prove that this D is actually a GCD. If we can prove this, we are done, because D belongs to this element. So D is of this form. And we just need to prove that D is GCD is equals to GCD A comma B. I'm going to stop here and ask if it is fine, if these statements are fine for you or not, or if there's any doubt here. Because and if you have seen this thing before or not. Please write it in the chat so that I know whether you're following it or not. Um, yeah, the proof is remaining. So like this is what I'm going to prove next. But like till here, is this clear? Like what I'm going to do, I'm saying that this is a set S of integers, a set S of positive integers. So I'm just going to write here. This is a set of non-negative, positive integers. So first I'm going to check whether that S is non-empty, and it is non-empty because you can see A belongs to S, you can see B belongs to S, and so on. So this S is non-empty. Once you know that this is non-empty, we are just going to use well ordering principle. It says that if what well ordering principle says, that any non-negative, any set of positive integers must contain a smallest element. So it must contain the smallest element. We call this the smallest element D. Now, if we prove that this D is equals to GCD of A comma B, we are done, because we know from here that D belongs to S, and all elements of S are of this form. So D must be equals to AX plus BY for some X comma Y. So we just need to show that D is equals to GCD of A comma B. I hope this is clear. So this is what I'm going to prove next, that D is equals to GCD of A comma B. So now we have to recall the definition of GCD. So what was GCD? we want to first show that D divides A and D divides B. And second, we want to say that this is the largest number that divides both of them. That's the definition. That's greatest common divisor. Just follow the words. Greatest common divisors. Even if you don't remember the formalism, you just have that intuition that, oh, this is the greatest number that can divide A and B. So what I need to show, first it divides A and B. And second, I need to show that if any integers divides both of them, D should be larger than that. If I can show that, I'm done. So this is what I'm writing formally in mathematical language, that, oh, D divides A and B, and then if there exists an integer that divides both of them, then that integer should be less than or equals to D. So now remember how you do the division. So formally, you have to do the division algorithm, right? So we have to now recall what division algorithm is. That's why I recall division algorithm on the first slide. So I want to show that. So first, so what I'll do, I'll just divide A with D. So A, I can write it in, and this is a set of, okay, again, look, this is a set of positive integers. So this implies that D cannot be 0 because this is a set of positive integers. So we can do the division. Again, that is very important because you are not allowed to do division by 0. Never ever try to do that. So you do the division of A with D. So what you'll do, you should be able to write it in this form where Q and R are Q quotient and remainder, and these are unique. And we have the property that the remainder is from 0 to D. Now we want to show that remainder is 0 because because we want to show that D divides A. So we will prove by contradiction. So we will here prove by contradiction. So what are we going to say? We are saying assume that R is not equals to 0. So once we assume R is not equals to 0, we can write A minus QD. We can write R is equals to A minus QD, right? You just take QD on the left-hand side. You can do that with integers. You can put QD on the left-hand side. And then this belongs to S, right? But we have that condition that R is less than D. But we have assumed that D is the smallest element of this set S, right? So this is a contradiction. We are finding an element in the set S which is smaller than D, which is a contradiction to our initial assumption that R is not equals to 0. So hence this completes the proof. Okay, I'm going to stop here and ask if it is fine with you or not, because let me know if there's any doubt here. Just say yes or no so that I can proceed. Or if you need me to repeat the argument. So this just proves that D divides A. So this step just proves that D divides A. Okay, cool. So similarly, you can proceed the same argument with B because there's nothing special about it, right? Like we could have chosen B first. So you can just repeat the same argument with B and then it follows that D divides B. Now we need to prove the second element. Now we need to show that this is the largest number that does something like that. So what I'm going to use here. So remember this exercise, right? If A divides B, A divides C, then A divides BX plus CY. I'm going to use this exercise here. So we know that if C divides A and C divides B, so we know that C divides AX plus BY. For any X and Y. For any X and Y, we know that C divides AX plus BY. It's just this exercise that I'm giving you as homework. Just do this exercise as homework. Like this is very easy. You should be able to do it. So then we know that, so okay, here we show that D divides A, D divides B, and we know that D is of this form because D belongs to this element S. And we know that C divides anything of this form. So we know that C divides D, and because C divides D, we know that C is less than or equals to D, and that completes the proof. You just need to write this in the notation. You just follow the notation and then this will be clear. And this completes the proof. And this completes the proof of the first important theorem, which is Bezo's identity. This theorem is very important if you will do some algebra later, like some group theory or something like that, ring theory, ideal theory. This comes up again and again and again in different forms. So, but the idea is more or less the same. This kind of contradiction, and then using well-ordering principle, it shows up in different formats in different areas of maths. But I'm not going there, just saying so that if you ever read this, you recall this proof. Like this idea is simple. Like you start with some well-ordering principle and you do the contradiction, and then yeah, and then you actually show that that completes the proof. Is this clear? And this is the first proof, so I just want to know if this is clear or not. If there's any doubt, if you want me to repeat something, just tell me. Okay, I guess there's no doubt. So I'm just going to give you an example. So suppose A is 6 and B is 15. Then you can actually take all positive linear combinations of, you can actually write a code for this. You can take all positive integer linear combinations of this, and you will see that this S comes out to be something like this, 3, 9, 6, and something stuff like that. And then you will actually find that the smallest element here is 3. And according to Bezo's theorem, this 3 is also the greatest common divisor of 6 and 15. You can take it as a small, like you can run it on your, and on, you can write a small code for it and you can check this. So just one small example. So why this theorem is important? This gives me a way of representing GCD as some equation. So this GCD, so okay, here I'm giving some formal statements telling what is GCD. Here I'm actually giving you a way of writing GCD. So that any GCD of two numbers you should be able to write it in this form. This will be clear later that why this is very important theorem. Okay, now there are again some exercises. So for this exercise is also similar. This is easy exercise. You see, you take two integers and you take a set T of their integer linear combinations of x and y, uh, of a and b. So what I'm saying is like this set is precisely set of all multiples of D. Not just that GCD is the smallest element, all the other elements here are actually multiples of this. This is actually important. Just try to do this. Like like any element of this form, D will be able to divide that. The greatest common divisor will divide this. I'm leaving it here. I'm not telling you much about the proof. Just try to use Bezo's theorem and the previous arguments, and you will be fine. So again, two integers, just again reviewing some notation. Two integers are said to be relatively prime if their GCD is 1. Just repeating it again so that you don't lose the touch. And actually, if GCD is, so basically what I'm saying, you should be able to write 1 as ax plus by for some x comma y in integers. Just recalling Bezo's theorem. I'll just keep on recalling things. So there exists some integers x and y such that you can write it. If you can write And if you can write 1 as this, 1 will definitely be the greatest common divisor. Take this exercise also as a homework. If you have GCD of a comma b is d, then GCD of a by d and b by d is 1. Just expand on the Bezo's theorem and it's done. Like basically you just need to write d is equals to ax plus by, and you have to divide by d on both sides, and it's done. And these are important exercises because this will be used in the proofs later for the theorems that I'm going to use. So again, the next exercise is A divides C and B divides C, and if GCD of A comma B is 1, then AB divides C. By the way, intuition wise, you can use fundamental theorem of arithmetic, but I'll prefer that you don't use it right now. You don't think of integers as something that prime numbers can factorize, because I want you to develop intuition for greatest common divisor separately of that. Once you think of prime numbers and how prime numbers divide things, this might seem trivial, but I want you to do this using only the things that I've defined above, not anything else. Like when you do this exercise at your home, just use all the things only defined before it. Don't use anything that I'm going to define later. That develops your intuition and how you prove things in maths. And Like this is actually intuitive. Just try to see for some examples and you'll see that this is very intuitive, but just try to prove it on your own. Now, if A divides B comma C, and if you know that there is no common divisor of A comma B, then it is very clear that A divides C, and this is actually Euclid's lemma. So this is again also not very difficult. You have to use Bezout's theorem and all those things that I've defined earlier. Just just two line proofs for that. And okay, so if D is GCD of A comma B, and if C divides A and C divides B, then C divides D. So earlier I'm saying if any number is dividing A and B, then D is greater than C, right? That is the definition of GCD. Now I'm saying if any number divides A and any number divides B, that number should also divide D. Actually, this can be used as an alternative definition. So in the definition of GCD, instead of C divides D, C is less than D, I can also say that C divides D. And these two definitions, this is alternative definition. And these two definitions are equivalent. And you can just play with it and you can actually prove it very easily. But this is actually important. This might seem trivial right now, but this definition will be used later in some non-trivial theorems. So if any number divides A and B, that number also divides D, your GCD. Not only that number is smaller than D, that number actually divides D. Okay, is everything clear so far? I've said a lot of exercises in a very small time, so I'm just taking like 1 minute break before proceeding next. Okay. So now the question comes is like I am telling you so far only about the theorems of GCD and properties of GCD. You might ask like how to compute that GCD. And for that we have the famous Euclidean algorithm. So what I'm going to do right now is I'm just going to prove a theorem that proves the correctness of Euclidean algorithm. And from the proof of this theorem, you can actually derive Euclidean algorithm. So I'm following a reverse way. People, rather than giving you the algorithm and then giving you the proof, I'm giving you a theorem. And from the proof, you can just easily get the Euclid's algorithm. And also one more important thing which will be useful is I will tell you how to compute inverses, multiplicative inverses, which is exactly what are you going to use in your blockchain course a lot. You will compute multiplicative inverses for modular operations a lot. And this is the standard properties and theorems that you're actually going to use again and again and again. So pay attention at this. So what I'm saying, if you can write A as QB plus R again, B is non-zero. If and there are two integers A and B where B is non-zero, and you can do the division. Then GCD of A comma B is actually GCD of B comma R. Okay, so it will be clear why I need this kind of theorem. So just following the proof step by step. So D is, let's say D is the GCD of A comma B. So let D is equals to GCD of A comma B, and so D divides A and D divides B. So D divides A minus QB. Remember the first exercise that I gave you? So A minus QB is actually R. So D divides R. Okay. So D divides B and D divides R. Now let C to be the GCD of B comma R. So we actually want to show that D is equals to, okay. So, and C, so we want to show C is equals to D, and we are done, right? So, sorry, oh, it's already written there. I'm sorry. So we want to show this, that C is equals to D. So D is the GCD of this, and C is the GCD of this. We already have D divides R. So, okay. So first of all, C divides B, C divides R. Again, following exercise 1, C divides B and C divides R. So C will divide A. So this follows that C is less than or equals to D. D divides B and D divides R, so D divides C. So this follows that D is less than or equals to C. This proves that both of these statements, D, C less than or equals to D and D less than or equals to C, proves that D is equals to C. Just following the definition, there's nothing there. Let me know if this is clear or not, if you followed all the lines in the proof or not. Just say yes or no in the chat so that I know and I proceed next. Um, mm, is it fine? Okay. Just read it once, or if you want me to repeat, I can repeat this. So I have taken D to be GCD of A comma B and D and C to be GCD of B comma R. And I need to show that C is equals to D. If C divides B and C divides R, then C also divides A. C divides B, C divides R, C will divide A. And okay, I need to write one step. C divides A, C divides D. C divides A, C divides B. This implies that C is less than or equals to D because this is GCD of A comma B. And D divides B, D divides R. This implies D is less than or equals to C because this is GCD of B comma R. Because it's the greatest common divisor of B comma R. So D is less than or equals to C. And if C is less than or equals to D and D is less than or equals to C, that actually implies D is equals to C because we are working with integers. That completes the proof. And why we need something like this? Because it will be clear. So we can continue doing this till the remainder is 0. So every time you're actually dropping the remainder. So like when you divide A by B, remainder is less than B. And then when you divide B by, okay, I'll show you. So you can keep on doing this. Remainder is actually decreasing in each of the steps. You can, at some point it will stop. So you can keep on generating these set of sequences. And this gives us a way. So at the end, it will be something like this, GCD Rn comma 0, because remainder is decreasing at every step. At some point it will be 0 because remainder is from 0. If you remember the property of remainder is 0, greater than or equals to 0 and less than the divisor. And at each step it is R is divisible by D. Where I'm saying R is divisible by D? Uh, D divides B, D divides R. Yeah, D divides B, D divides R. Oh, sorry. I understand what the confusion is. Take B and R as two numbers, and D divides R means when you divide R with D, you might have some. So when you divide R, so R Q1 D plus some R2. This R2 is 0. So R should be okay. So I'm saying this is what R should be when I'm saying D divides R. Is it clear? Okay. Like think of them as separate numbers. Don't confuse them with the first remainder. Every division has a separate remainder, and you have a sequence of divisions happening. So you have remainder R1, then remainder R2, and then you can keep on doing this. At some point, it will be 0 because at each step you're yeah. So what am doing here? I will show you division algorithm in a minute so that it will be clear, but just be here for a minute and in the next page, it will be clear what exactly is happening. You can actually get a sequence of the following equation. So you divided A with B and you get some remainder. Then you can divide B with R1, and then you get some remainder R2 and so on and so forth. And at some point it will stop, and it will stop when one of the remainder is 0, and this GCD of Rn comma 0 is actually Rn. So you have a way of computing this, and this is exactly Euclid's algorithm. I'm just going to go to the Euclid algorithm. It's much clearer then. So what is Euclid's algorithm? So you have two numbers, A greater than or equals to B greater than 0, as always assuming that B greater than 0, and never going to divide by anything which is 0. That is not allowed at all. So you first divide A with B with quotients Q1 and R1. R1 is less than this. Now you take this as B and you divide B with R1. Now you get R2, and you can continue doing this. And at some point this will stop because at each step here, R2 is decreasing. Here, R3 is decreasing. But you are starting with an integer. It will stop at some point because all these numbers are decreasing. So it will stop when R n plus 1 is equals to 0 here. This is the stopping point. And this Rn, the final Rn that you get here, is the GCD of A comma B. This is Euclid's algorithm. And that's what people do recursively. When you see the code of writing the GCD, they do this recursively. They just use these things. And you can write this recursively. Take that as an exercise. Write a small code on this, like how to compute GCD of two numbers recursively using Euclid's algorithm. So this just proves that Rn is the GCD of A comma B. Okay, the story doesn't end here. We actually want to write, if you remember the Bezos theorem, the most important theorem I've said so far, I've presented so far. So in that theorem, we said that GCD, Rn is the GCD of A comma B. We said that you should be able to write it as in the form Ax plus By, where X, Y are integers. This is important. It will be clear why it's important, but just be here for a minute with me and you will see in the next part of the lectures why it is important. So you should be able to write Rn as Ax plus By. But can you find these X and Y using this Euclid's algorithm? Like how to find these X and Y? Like actually you can do this. You can use this, all these steps. You can using all these steps, you can actually find X and Y. And this representation of GCD as Ax plus By is really important. So what are we going to do? So we start with Rn and we'll just go one step ahead above. It's like Rn minus 2, Qn, Rn minus 1 plus Rn, right? This is the first step above. So Rn can be written as Rn minus 2 minus Qn minus Rn minus 1. You just take this term on the left hand side, right? And you can keep on doing this. So you see, now Rn can be written as Rn minus 2 plus this is integer plus some terms, and this is again integer. All of these things are integers. Qy's are integers, Ri's are integers, A's, all of these things are integers. So Rn can be written in terms of Rn minus 2 and Rn minus 3 with integer coefficients. Now keep on doing that, and finally at some point you will just reach to this step A comma B, and you should be able to write it as Ax plus By, where X is something that will be of extended form like this. You can do induction and you can prove this. So I'm giving you an algorithm of, from Euclid's algorithm, I'm giving you another algorithm, like just from the information of Euclid's algorithm, you can actually write it in this form, Ax plus By. And this will be clear why this is important when we are talking about multiplicative inverse. But keep this process in mind. And okay, there's one thing, just look, extended Euclidean algorithm. Take this as an exercise too in Wiki and figure it out. This will be important for your blockchain course a lot. So I've given you the concept of that, but when you go back after this lecture, before tomorrow's lecture of blockchain, just look extended Euclidean algorithm in Wiki. Then the concept is exactly what I'm saying. It's just in a much more formal way. So if k, and I'm going to give you some more exercises. So if k is greater than 0, then GCD of ka and kb is k. You can actually take k outside. And then GCD of ka and kb is k multiplied by GCD of a comma b. How are you going to prove it? Use Bezos theorem. Anything in GCD, any kind of property that you might see in GCD, the first thing that should hit your mind is Bezos theorem, and the second thing that should hit your mind is the two formal definitions of GCD, that it divides A and B, and this is the largest number that can divide A and B. And you will be able to prove all the things that there can be about GCD. The next exercise, it's an important one and also a fun one. So I have not defined LCM, but this is least common multiple. And the way I've defined greatest common divisor, you can define least common multiple. Again, take it as an exercise of what should be the definition of least common multiple. Like try to give a definition on your own, try to formalize that on your own. So given two integers, GCD of a comma b and least common multiple of a comma b should be actually the product of GCD and LCM of AB is actually the product of two numbers. So this is uh, I'm again giving you one more exercise. Uh, and after you write this definition and then prove and then proceed with exercise. Okay. Is there, okay, now we will switch to classical results, but before that, let me know if you have any questions so far in these three sections that I presented. Or if everything is clear, just say yes in the chat so that I know everything is fine for you. Oh yes, like I think I will have more sessions like where I will introduce Chinese remainder theorem, and I think I will need more than one session to finish this lecture. I think like there are lots of classical and fun results that I wanted to share, and it also depends upon like if you have more doubts, we can also have doubt sessions and stuff like that. Like okay, so I will go to the classical results of number theory. Some of the results you might know already, and some of these are celebrated results. And okay, so first, so is everything fine, right? So then I'm just going through this session, and I think I might stop in the middle of it. Okay. So fundamental theorem of arithmetic. This is the second most important theorem after Bezo's theorem. This is the next important theorem that I'm telling you. I'm not proving this theorem. If you're interested, you can look up the proof. The proof actually follows by the induction, and you have to use some properties of greatest common divisors and stuff like that. But it's not very difficult, but it's an induction. It will take a lot of time, so I'm not going through. It's exactly what you have known from your childhood or middle school or primary school, that every integer n is either a prime number or it can be written as finite product of prime numbers with powers, positive powers, where ki's are the positive powers of this. So every integer n should be able, you should be able to write it as, you can factorize it as prime factors, and each prime factor has some multiplicity. That multiplicity is ki. So either your integer is a prime number, and if it is not a prime, then you should be able to write it as product of primes. That what is the fundamental theorem of arithmetic. And I hope you know what prime number is. Prime number is a number which doesn't have any other divisors other than itself and one. Examples 2, 3, 5, and so on. Um, then there's another important theorem that says that there are infinitely many prime numbers in integers. Like it's also the classical result. It's from Euclid. Um, just saying it for the sake of completeness. You might need it at some point in the proofs of your crypto systems. Okay, so I hope these two theorems are clear to you. I'm not giving proof of both these theorems. If you're interested, please look it up. You can just read the proof, or you can also try to prove it on your own. For this, the proof is very nice. This theorem, the proof is very nice. It will be fun exercise for you if you can do it. Okay. Cool. Now I will need to define some more notations. The first notation, similar to the first one, where I've defined A divides B, and now I'm going to the modular arithmetic. So I'm going to just review the modular arithmetic if you already know, and if you don't know it, then this is a good chance to learn it. So for integers n, I'm saying n is greater than or equals to 0. Two integers a and b are said to be congruent modulo n and are written as a congruent to B modular N if N divides their difference. That is, there exists an integer k such that A minus B is equals to, oh, I'm sorry, I think I just need to, there's a mistake from my side. I think it's just positive. Yes. Because we cannot divide by 0, so n divides a minus b, there exists k such that a minus b is equals to kn. So basically, what you can also think of it as remainder. So when you divide a with modular n, you just keep the remainder n. For example, when you divide 24 by 7, you get remainder 3. So 24 is 3 modular 7. The 24 is congruent to 3 modular 7. Similarly, when you divide 6 by 5, you get remainder 1. So you get something like this. And now I'll give you some, and you can keep on doing this. And like, for example, 4 is equals to 0 modular 2. Because when you divide 4 with 2, you don't get any remainder. And you can also see it as, so you can also see, using the above definition, 7 actually divides 24 minus 3, which is 21. 7 divides 21. 5 divides 6 minus 1. 2 divides 4 minus 0. You can keep on doing this. So the intuition is you're taking the remainders. So if I give you two numbers A and B, and I'm just writing the remainder of after the division, and you write it in this modular form. This notation clear? Is this fine? Because like everything from this will be built upon this notation. If this is not clear, just ask now, because if then afterwards it will be much more difficult to understand things, because I'm going to use this notation again and again and again. Just say yes if it is clear, then I'll proceed. Or if you want me to repeat something. Okay, I assume it's fine. Okay, so I'm going to give you some properties of these modular arithmetic. Take all of these as exercises. This is nice. You should be able to do it. If you have already seen it, it's nothing. Just review it. If you have not seen this before, just take all of these as exercises. Sorry. So okay. So first of all, A is congruent to itself. Second, if A is congruent to B modular N, then the B is congruent to A modular N. I mean, the order, you can switch the order because there's nothing special about the order. That's what I want to say. Third, if A is congruent to B and B is congruent to C, then you should be able to say A is congruent to C. Like it's transitive. Like A is congruent to B, B is congruent to C, so A is congruent to C. Fourth, how will you, I'll first give you all the properties and then I'll give you a hint how will you prove this. So if A is congruent to B modular N and C is congruent to D modular N, then you should be able to add this. Like if you have one identity here, you have one identity here, you should be able to do the normal addition as you do in normal arithmetic. So like in normal arithmetic, when you're not doing the modular thing, if x is equals to y and you have like z equals to x1 equals to y1 and you have x2 equals to y2, you should be able to add it. X1 and the same thing holds here. So if you have this equality, this congruence here, you should be able to add it. If you have this congruence here, you should be able to multiply it. That's what arithmetic. So we are defining a new arithmetic. We are defining a modular arithmetic, and it follows similar kind of rules. That's what we are establishing now, and you have to prove them. This doesn't come out for free. You have to prove all of this. And the fifth one is if A is congruent to B modular N, then A plus C, and there is another integer C. It can be any integer. What I'm saying is like you should be able to add C on both sides, and you should be able to multiply C on both sides, and it should be again be congruent. Again, following the same intuition as the normal arithmetic that you do with integers. Modular arithmetic follows the same intuition. The last one is like if you have A comma, if you have A and B which are congruent modular N, I'm saying k power of them should be any k power of them should be congruent modular N. How will you prove this? Just use this. You just use this and do the induction. Just use this. Once you have proved this one, then you have to use the induction and then you're done. How will you prove all of these properties? Just follow the definition. Just follow this definition. and you're done. Don't overthink it. Just follow the definition. Once you have proved it, I would also suggest you to like play with them, like take small numbers and like take some numbers A, B, and N and try to see and try to compute the remainder again and again and see whether you're forming an intuition. That's how you form intuitions. Uh, First you play with examples and prove, and sometimes you prove and play with the examples. But like both of the process is really important to have intuition for anything mathematical that you will study. Okay, so keep these properties in mind. I will come back to these properties whenever I'm using it, but just please go through them uh, if you have not seen them already. Okay, now the final part. I think I will give you the intuition and let's see how much we can go, which is the multiplicative inverse. We need this multiplicative inverse for, okay, we need this multiplicative inverse for defining primitive root, right? And which you have used in last two lectures of your blockchain, like in your systems. So you have only used primitive roots for prime numbers, but primitive roots exist for any integer and uh, under some conditions. And for that, we need some theory. And so far, I've been building up that theory to be able to do it for any natural any integer n with with certain assumptions, and you will need that in your crypto systems. So all of this theory will be used. Like it's not just it's fun, but it will be used for your course. So before I proceed, I need to like give you some intuition about inverse and multiplication. So I hope everyone knows rational numbers and rational numbers are, right? Like any integer of the any number of the form m by n, where n is not equals to 0, and m and n are rational numbers. M and n are integers. So what is the difference between rational number and integer? Like, can anyone say anything? I hope you have not seen the entire slide, but can you give me a difference between these two things? Like if I have a set of integers and if I have a set of rational numbers, we have arithmetic defined for both of them, and the arithmetic is pretty standard. But there is one clear difference between that. Can you tell me that difference? Just use the chat, or you can just say things and I'm going to give you some time, like 30 seconds or something. Just think about it. Like what separates rational numbers and integers, like property wise? Like what is the property that rational numbers have that integers don't have? Like you have a set of integers and you have for rational number p by q and q is not an integer if q divides p. Yeah, integers is a subset of rational number. That is correct. But I'm asking in terms of arithmetic. Like there's one arithmetic operation which is different for rational numbers. Yes, yes, exactly. Closed-ended division. Exactly, you got it right. So closed-ended division for non-zero rational numbers, right? So if you have a rational number which is not zero, you can take the division of it. You can invert it. X inverse 1 by x, which is equals to n by m. If x is not equals to 0, this is m by n, this is n by m. I'm sorry, this is n by m. And this belongs to rational number. So if I have in the set of rational numbers, all non-zero rational numbers, inverse is also a rational number. But that doesn't happen for integers. So for example, 2 by 3 is a rational number, and 3 by 2 is also a rational number. But that doesn't happen for integers. Like clear example that can come to your mind is just take 2. 1 by 2 is a rational number, but it is not an integer. So 2 inverse of 2 doesn't exist in integers. It actually exists in rational numbers. Okay. And same question you can ask about the modular arithmetic that we have been doing. Like you can ask, okay, so for modular arithmetic, I need to, yeah. So this is the notation that I'm going to use for modular arithmetic. So when you are doing modular arithmetic, modular n, I'm going to use this z mod nz. This essentially means all the integers of 0, 1, and minus 1. These are all the remainders that you will get when you do the division by n. You already know the arithmetic of this set. You can you can take any two numbers, you can add, it is there. You take any two numbers, you multiply, it is there. But the inverse is not, what about the inverse? Like, it's not as clear, right? Like as integers is like, can you say anything right now? it's not very clear. Like if you already know the theory, then it is clear. But like without knowing the theory and like without having the examples that like you need to try some examples and then you understand. But like first of all, what do I mean by inverse? We even need to understand that. So for that, I'm going to develop the theory now. So when n is a prime number, p, we have z mod pz, which is 0, 1, 2, up to p minus 1. And in this, every number other than 0 has a multiplicative inverse. And when I say multiplicative number inverse is like x belongs to z mod nz, there exists a y belongs to z mod nz such that x and y is equals to 1. Basically, I'm saying if basically this y is x inverse. So if there exists another integer y inside this set z mod nz such that xy is equals to 1. What I'm saying is in z mod pz, every number other than 0 has a multiplicative inverse. And you would be asking, what is the reason for that? Like, you have not given us any theorems or proofs or anything like that. So I think I'll just end this lecture here by giving a trailer for what is coming up next for the next sessions when we meet again, and the more general theory that we need to cover. So this is like the famous theorem by Fermat. It's called Fermat's little theorem. So what it says is like this. If P is a prime number and if P doesn't divide A, so like P doesn't divide A also means that A is not equals to 0 mod P. Just different notation. Like, oh, sorry. A is non-zero modular P. It's just saying A is non-zero modular P. So, yeah, in other words, A is, oh, sorry, I'm sorry. I'm done some mistake. A is not zero modular P. I need to erase this. And okay. So then it says that A power P minus 1 is actually equals to 1 modular P. So you take P minus 1 powers of A and it will always give you one remainder when you divide by P. So for all A which are non-zero lying in this set, actually AP minus 2 is its inverse because you can write AP minus 1 as A dot AP minus 2 equals to 1 modular P. And this is what is. So we have inverse for every element using this theorem. And this makes your life easier for primitive roots for P. But when I ask for any integer n, you need some more theory. So let's just do this. Let's just do some examples and then I will finish this lecture. So Z mod 3Z, what it would be? 0, 1, 2. I mean, all the remainders that you get after division by 3 are 0, 1, and 2. So one has its own inverse. Like for 1, it is already 1 multiplied by 1 is 1, right? 1 multiplied by 1 is 1. So 1 has its own inverse. But like you have to check for 2. And for 2, we need to do Fermat's theorem 2. And here P is actually 3. So 2P minus 1, which is actually 2 square, which is exactly what I'm doing here. 2 square is equals to 1 mod 3. So you see every element other than 0 has one multiplicative inverse. This is what I claimed here. Every number other than 0 has multiplicative inverse and Z mod PZ. And but then what about any non-negative integer? You might ask, oh, is this not true for any non-negative integer? And I've been saying no, but you might ask, okay, give me a counterexample for that, right? Like if I'm saying something is not true, then the natural thing to do is to give a counterexample. So the easiest counterexample that comes to mind is 4. 4 is not a prime number. And this is the set 0, 1, 2, 3. And you can see 2 is not invertible. Just try to find the inverse. Like when you multiply 2 with 1, it's 2. When you multiply 2 with 2, it's 0. When you multiply 2 with 3, it gives you again 2, modulo 4. So 2 doesn't have an inverse in this set. So what shall we do? And when we need more theory here. And I think this is where I'm going to end. And what is coming up next is like some more theorems, and I will give you the theory when the multiplicative inverse exists. And then once you know the theory of multiplicative inverses for integer n, we will go towards primitive roots, which is exactly what you need for your further lessons in blockchain. Okay, so let me know if you have any questions here. I will share the lecture notes with you, and also the video will be available.